Module 9, Composition and Inverse. This is going to be a short lesson because the majority of the topics here are reviews. The first topic to review is the matrix associated with a linear map, and let's review that. Let V and W be vector spaces with bases v1 through vn and w1 through wm respectively. So the first vector space is n-dimensional and the second vector space is m-dimensional. Can you see these indices? Let me expand the font. Okay, now it's a lot better. N-dimensional to m-dimensional. So the domain or the original vector space is n-dimensional. And then the target is m-dimensional. Then any linear map from V to W is associated to a unique m by n matrix such that the linear map W equals to L of V corresponds to the matrix equation Y equals to AX. Here, A is m by n matrix. M is the dimension of the target, n is the dimension of the domain or the original vector space. And here, as you can see from the color coding, the column vector x is a coordinate vector of V, and the column vector y is a coordinate vector of W. Therefore, this is n-dimensional and this is m-dimensional. This is what I'm talking about. N-dimensional, m-dimensional, so we have to have m by n matrix. Or I can be even more straightforward like this. This is m-dimensional column vector, you can clearly see that. And here is n-dimensional column vector. And this one you can count m by n matrix. And then, what do you mean by those x1 through xn and y1 through ym? If you remember everything, that's great. In case you don't remember, let's review. After all, the purpose of this is to review. So let's go ahead and do that. You can write a linear map L from V to W. This is equivalent to that. And the advantage here is just getting this input-output model. So this is equivalent to that. And then this expression, now element of V, arbitrary vector V, is going to W, and this expression here is equivalent to this, W equals to L of V. So this expression and that expression are actually the same, just written a little bit differently. This one is a little bit more algebraic, it looks like an equation, and this one looks like an input-output model. So V is going to W due to this map L, and V can be written as V belong to capital V, and that has bases v1 through vn. So any vector there can be written as a linear combination of v1, v2, v3, all the way over to vn, like this. And this expression is unique because this is basis. The linear combination exists if this is the generator, and then the uniqueness comes from the linear independence, so this expression is unique. This unique expression is called a coordinate expression of this V, and that's what this x1 through xn is all about. Same goes for y1 through ym. So if you get W, which is L of V, then it belongs to capital W, so it should be generated by W1 through Wm. So we have linear combination y1 w1 plus all the way over to ym wm, and that linear combination expression is unique, and that's called a coordinate expression, and it's customary to express it as a column vector y1 through ym. Please note that this linear combination is the same as this matrix multiplication, so row times column, and it's customary to use column vector expression. It's more convenient that way. Same thing goes over to y1 through ym. And that's how they're related. M-dimensional, n-dimensional. This is m by n. Okay, all right. Now we talked about x and y. Now let's talk about a and let's talk about the matrix A. How do you get this matrix A? You get it by the basis vectors v1, v2, v3 all the way over to vn, and then take their images and get L of v1, L of v2 all the way over to L of vn. Now these image vectors belong to target W, so they can be written as a linear combination of W1, W2 all the way over to Wm. And that coordinate expressions kind of like these. These expression, actually not that. These expression exist for all those basis vectors, v1, v2, v3 all the way over to vn. And let us call them y1, y2 all the way over to yn, and they're all column vectors, so coordinate vectors. So first column, second column, all the way over to the last column, and that's a matrix expression. How many columns are there? v1 through vn, that's where we started. So it's the same as the dimension of v. Now, how many rows are there? That's because the dimension of each column vector, so each linear combination of the image vectors, it should be m, because that's the basis. And that's how you get m by n matrix. Well, we ended a very thorough review here, and that's going to be helpful, especially those indices, which can get confusing. Now let's go to composition. Oh, excuse me. I need a little bit bigger font here as well, because we have to look at the indices very carefully. You see, we have u, v, and w be vector spaces, but what are their dimensions? Their dimensions are n dimension, m dimension, and l dimension respectively. So backward, nml, or backward, lmn. And then the linear map from u to v, n dimension to m dimension, and the linear map from v to w, m dimension to l dimension, will be associated to the matrices A and B, which is m by n and l by m. So this is going to n dimension to m dimension, and this is m dimension to l dimension. So you see, n to m, that's A, and then m to l, that's B. Now if you compose G circle F from n-dimensional space all the way over to l-dimensional space directly, and that's associated to B times A, because after all, each linear map is matrix multiplication to the left, so multiply by A first, and then next multiply by B. And do we have correct dimensions? It'll turn out yes, because let's see, B times A, B times B, which is L times M, times A, which is M times n matrix. And matrix multiplication is well defined because these two are the same. And then this product matrix is going to be L by n. So these two collide and disappear, and we have L times n. So yes, indeed, it is well defined. Everything looks fine. This is red, and that's blue, isn't it? Associated to blue map F and red map G, respectively. So in terms of matrix multiplication, it is well defined. In terms of input-output, it works fine too. From U to V, so that's F. From V to W, that's G. And from U to VF, that's multiplication by A. And after that, multiplication by b. So if you use the associativity rule, then multiplying by matrix b times a to x. How about the dimension? This is n dimension. Let me copy and paste this thing. This is n dimensional. And then this is this whole thing. This whole thing is now m dimension because A is, you see, m by n matrix. And this is n by 1 matrix. And then what do you do now? We multiply L by M matrix. And then this whole thing, as we checked before, is M by N. M by, 1. So M dimensional. So in the end, what do we get? We got L dimensional vectors. So M collide. So L dimensional column vector. So, okay, we got what we wanted. Oh, too many indices is a bit too confusing, so let me remove that. Just remember the conclusion. Because we went through, everything makes sense. So we verified everything. So, all right, from this point on, we're going to be just using it. How about the inverse? Well, it's kind of like composition map, except that we have to come back to the original. So we have to start and multiply by a, and then multiply another thing so that we have to get back to the original. And that's to be the general case for all kind of x value, not just a single x value like the origin, for example. Zero vector always stays zero vector, no matter what. So even if this matrix multiplication is something very strange, zero will stay zero. But that's not what you're looking for. This is true for arbitrary x. For that purpose, this has to be identity. So what can I multiply to get an identity? It's an inverse matrix, of course. So yes, matrix multiplication, the inverse map is associated to inverse matrix. Well, so far so good, but there's just a little bit of problem. Just a little bit of a problem, which we will fill up shortly. Now, we know the inverse map exists because we assumed invertible. You see, inverse exists. If it is one-to-one map, then yes, inverse exists. Inverse from the range, coming back to the domain. But then again, is the inverse map also a linear map? That's a big problem. Is it also a linear map? If it is not a linear map, then there may not be a matrix associated to that at all. Then we have a problem. If we know this is a linear map, inverse is also a linear map, then there got to be a matrix associated to that. And then, of course, that matrix multiplication will yield identity. So it's an inverse matrix. Everything fits. So the one thing that we didn't do is whether the inverse is also a linear map. Okay, let me explain this again. If inverse were not a linear map so that the matrix representation does not exist, then everything is moot. We cannot use this kind of argument. If we know that inverse map is also linear, then there is a matrix associated to this inverse map, and whatever that matrix is, that matrix multiplication will yield an identity matrix, so it's an inverse matrix. Everything fits well if the matrix exists to begin with, or in other words, the inverse map is linear to begin with. If we prove that, then we are through. And that's what we are going to do now, shortly. Okay, first, one-to-one, if and only if kernel is just a zero vector, and we went through already. All right, no problem there. Now here we go. Let V and W be vector spaces and let V to W be a linear map. Let L from V to W be a one-to-one linear map. Then the inverse map is linear. We know the inverse exists. So from domain to target is too big, so we have to get down to the range or image back to the domain. So the inverse map exists. Now, is this linear? That's what we have to prove. So basically, this is what we have to prove. We know inverse exists, okay? This is one-to-one map. So L inverse of the linear combination A1W1 plus A2W2, can this be separated so that linear combination is preserved? If so, then answer is yes. So this is what we want to prove. This is what we have to prove. And we are going to start from the left-hand side and work something out, and then we are going to go to the right-hand side. But of course, we need some preparation. Ready? Okay, let's get to it. Let's have W1, W2. So let's take the inverse map. So W1, which I color code as blue, and W2, which I color code in red, and take the inverse. Let's call it V1 and V2 respectively, blue and red. Consequently, W1 is L of V1 and W2 is L of V2. Clear. And in order to see things better, I'm doing a color coding. All right, can we start here? Actually, not just yet. Instead of starting from A1W1 plus A2W2, we have to start from A1V1 plus A2V2 here. See? L of A1V1 plus A2V2 and L is a linear map. This is forward map. So we can separate the linear combination. So we can separate all these out, and V1 part blue and V2 part red. So far so good. I didn't do anything spectacular. I just used the property of the linear map and separated the linear combination. And let's go back to previous naming. Blue is blue. L of V1 is W, and L of V2 is W2, that's red. So far so good, just going back to all that. Now, the preparation is done. Let's go back to this conclusion here. This is what we have to prove, and let's prove that. Let's start from the left-hand side, and here the left-hand side, and let's continue using the same color coding. W1 is red, W2 is red. W1 is blue, W2 is red. And then let's go to this. And did you just prove A1W1 plus A2W2 came from A1V1 plus A2V2? We just did. So if you take the inverse map, this is what we're going to get, of course. So that. You see, we just use this one backward. So this went back to this. That's the inverse map. So we got up to here. And then let's go back to these. And then my V1 is L inverse of W1. V2 is L inverse of W2, blue and red respectively. And that completes the proof. So the only thing that we didn't prove, we just completed. Inverse map exists, of course, yes, because this is a one-to-one map, but inverse is also linear if the original is linear, and we just did it. Okay, we have just a little bit of time left for mentioning 2.3, and all these are gonna be left to the students. Think about the rank theorem, and some of them may be homework problems.